Hey, this is Mr. Mitchell with a video on work and energy. Here are your questions. Work. In scientific terms, you only do work when movement takes place. So with this guy right here, he can push and push and push and push on this wall, and he's not going to move it. So according to scientific terms, he has not moved anything. He has not done any work. You actually do more work lifting a feather than you do in pushing up against a wall. And you probably figured out there is a formula for work, and it happens to be here. Now, just a couple of, one thing to remind you, not to really remind you, but to kind of say, forces create work. And work is only done by the part of the applied force that acts in the same direction. So if you have some kind of buggy here, maybe a Red Ryder wagon, you're going to pull the wagon that way. But if you're standing here and holding it right here, you're actually going up. The part of this that is going up instead of sideways is not going to be doing any work. It's only the part that is going sideways in the same direction as the wagon, which will be doing work. So just kind of want to clarify that. Now let's get back to this work formula. Work equals force times distance. Force, you may remember, is measured in newtons, and that's mass times acceleration. We've already covered that. So newtons is what mass is in, is what the force is in. Not mass, but what the force is in. And distance is going to be meters. I don't think I have it right here. So work is going to be newtons times meters, and that's going to be something called a joule. Whenever you find work, you're going to have it in terms of joules. So let's try to do some of this down here. We have a forklift that moves 34 meters, carrying a 1023 Newton box across the warehouse floor. How much work is done? Work equals force times distance. And force equals, looks like 1023 newtons. And distance looks like 34 meters. So 1023 times 34 is going to be what? 1023 times 34 equals what? Looks like 34,782. 34,782. 34,782. 34,782. What? It will be joules, which is a capital J. Well, there's a little bit more to this work concept. There's a term called energy, and you've heard of all kinds of energy. But scientifically, energy is the ability of a person or object to do work. Now, when you do work, energy, right here, is transferred. And we'll talk a little bit more about those transformations from one kind of energy to another in a little bit. But both work and energy are going to be measurable stuff, and it's going to be measured in joules. So let's talk about one kind of energy. One kind of energy is going to be called kinetic energy. That's the energy of motion, where you actually are moving. Like this guy on the skateboard. He actually is moving. Now, we said earlier that you have to have movement. You have to have movement to be able to have work done. But there's something called potential energy, which we'll talk about in a little bit, where you have the, I guess, the potential of work done. But we'll get to that. Let's take a look at this ball up here. As it sits on top of this hill, it does not have any kinetic energy. But once you start rolling it down the hill, it starts to pick up a lot of kinetic energy. And by the time it is way down here, it has a whole lot of work that it has actually done. So there actually is a formula, as you probably guessed, about kinetic energy. Seems like there's a formula for everything. But kinetic energy is in joules also. Mass, 1/2 the mass, times volume squared. So let's take this problem right here. Cat, the mass is 12 kilograms, and the cat has moved 8 meters per second. So you have moved the cat So kinetic energy equals 1/2 the mass, which is 12, times 8 squared. And I didn't put kilograms in there in meters per second, but that's what that is. Okay, so kinetic energy equals, I'll multiply 1/2 times 12, and that will make 6. And I'll multiply 8 times itself, which will make 64. So the kinetic energy is just multiplying those together, which I can do right here. 64 times 6, 24, 38, looks like 384 joules. That's kinetic energy, which is actual energy of motion. And that's going to contrast with potential energy. Potential energy is energy of position. Now let's see if you can get this concept. Look at this boy right here. He's about to pull a slingshot. As of right now, the ball or the rock, whatever he has, is not doing any work. But all he has to do is let go, and it slings forward at a very fast pace. You could say that there's a lot of potential for energy to take place. So the rock or ball that he has right here has much more potential energy than it does laying on the ground somewhere. This lady here has a bowling ball. The bowling ball is in her hand and ready to be rolled. It has a potential to do energy, much more so than the ones that are sitting on the rack back behind all the spectators. Even here, you have an apple that is just there on the tree. What energy might it have? It has the potential to drop. And whenever it drops, it moves. So the movement is going to be some actual energy. So in all three cases, we don't really have any work going on, but we have the potential for that work to go on. It's the potential energy, energy of position. Let's go back to this that we've had. We have this ball that's on top of a hill. It has a lot of potential energy because all you have to do is just push it one way and whee, it goes down the hill. Same thing if you go the other way. It has more potential energy than it does if it's just sitting here at the bottom of the hill. So, potential energy plus the kinetic energy makes up what's called mechanical energy. Mechanical energy is the actual energy that you see, including the potential that it has. Now, what we're going to say is a little bit heady, but whenever this ball is at the top of the hill, it has zero kinetic energy, and it has a lot of potential energy. We'll put X because I don't know exactly how much it is. As it is going down the hill, it gradually loses potential energy, but gains kinetic energy at the same exact rate. Once it gets down to the bottom of the hill, it will have zero potential energy and all the X, or I'll say the X amount of kinetic energy. So what's going to happen is you have a law of conservation of energy that says matter is neither created nor destroyed in motion, and I don't know why I put matter, because it is energy. Energy is neither created nor destroyed in motion. So you have the same total mechanical energy at the top of the hill, going down the hill, and at the bottom of the hill. Now there's something else that we have here that seems to only apply to this apple here. It's called gravitational potential energy. And yes, there's a formula for that. Gravitational potential energy is, well, it calculates the amount of potential energy of this apple that is falling. It's just like calculating other kinds of energy, except you know what the acceleration will be. going to be 9.8 meters per second squared. We've learned about that. So if you have the mass of an apple, G is going to be 9.8, gravitational constant, and the height from where it's coming from. Then you can calculate the gravitational potential energy. Why don't we do it? Here's the mass of the apple right here. We have GPE equals 0.2 kilograms times 9.8 meters per second squared times 2, which is the meters. GPE equals, and why don't I just calculate some of that? We have 0.2 times 9.8 times 2 equals 3.92. So the gravitational potential energy is 3.92, and you know what it's going to be in. It's going to be in joules. Hey, let's look at something else here. In most energy transformations, some energy is transformed into heat by friction. For example, this guy right here who's riding down the hill, the heat is going to be at his wheels. Those wheels are going to be hotter than they were whenever they started. So yes, you will lose a little bit of that energy, but energy is not lost overall. Okay, the final thing about this video, final couple of things, is there are other forms of energy. We have thermal energy, which is energy due to molecular motion. You can't see it, but even solids are moving. The desk underneath you, or the chair that you're sitting on, has some kind of molecular movement to it. We have chemical energy, and what I have here is a chemical equation where you have a chemical change. So whenever you have some kind of chemical change, and wow, we'll talk a lot more about those in a couple of months, but when you have a chemical change, you're going to release some energy. Nuclear energy, whenever you split the atom for usage in bombs or for usage in power plants, that is a kind of energy. Electromagnetic energy is more than just energy of the sun, but that radiation from the sun is an example of it. So we'll put that there as our diagram. Final thing, energy can transfer from one kind to another. Now before we talk about this interesting picture here, I'll say that if you rub your hands, you're converting actual mechanical energy into thermal energy. Now, if this lady were to actually eat this entire hamburger, it doesn't matter, because even if the lady eats some of the hamburger, her body will convert the chemical energy stored in food. Yes, whenever you eat food and digest, you have a chemical reaction. Your body converts that chemical energy to thermal energy and then to mechanical energy in muscle movement. Whenever she moves her muscles, that is an example, or that is actually using energy that can be traced back somewhere to something that she ate. Well, I hope you've learned a little bit about work and energy.